Welcome. I'm talking about vulnerability discovery, finding vulnerabilities in embedded software. That has been a research thread that we have been working on for several years, and I hope to tell you a little bit about why I'm excited about it and some of our more recent results. All right, what are we talking about? We're talking about a few things that we have done on looking at vulnerabilities in embedded software. In particular, I want to talk about finding a special type of vulnerability that involves multiple binaries in firmware, and then looking at binary blob firmware, and we try to use fuzzing and rehosting and find interesting vulnerabilities in binary blob firmware, which is generally pretty hard to analyze because it doesn't have the typical structure of an operating system, the typical structure of a program that might use system calls, or what you're used to when you would analyze a Linux binary. So why do we do this? I just want to spend like a couple of minutes on setting up the stage. Why is it interesting to look at IoT security, embedded software security? Well, first, there are a lot of these devices out there. Everybody, of course, has seen many of those devices. And a lot of those have some very relevant security implications, right? If you have an automated lock, or if you have cameras that can monitor things in the real world, that can monitor your apartment, your office, that can open offices, there's just a lot of security and privacy sensitive issues related to those devices. And so it's not a surprise that we have seen many security problems related to this. So, we have seen a Mirai botnet that has infected millions of IoT devices and has caused a lot of denial of service attacks. We have seen increasing reliance of critical systems on those embedded and IoT devices. And we've generally seen that the security of those devices is pretty poor. So we have sort of this combination of devices that are relevant, devices that have access to real world systems, devices that have access to a lot of sensitive data. And on the other hand, the security state of those devices is generally poor. They have a lot of vulnerabilities, and it's not as well tested, not as well battle tested as your normal desktop application or or browser or something like that. So I think it's an important study topic, but another question that you might ask yourself is, what's different about it, right? So if you look at vulnerability research, that has, of course, a very long history, right? Decades of attempts to use some kind of program analysis, both static and dynamic program analysis, to find bugs in software and then find security vulnerabilities in software. So is there anything different when we look at IoT devices, when we look at firmware, that makes that research maybe novel, maybe interesting, maybe different from what we have done for many, many years on, let's say, the normal, more regular software? And I think the answer is yes. And I think what we will see is that some of our analysis techniques are actually adjusted or needed to be adjusted to work in this new space. Right, so we could not use our standard techniques of just looking at, for example, source code, right, using static source code analysis. And the reason is, typically you don't have source code available, right? You just have the binary code. It's actually even hard to get to the binary code. If there is some piece, like you have some hardware device and it runs some firmware, like how do you get the binary out of there, right? It's even hard to get the binary out of there. And when you get the binary finally, you notice that it's not just like a nice modular piece of encapsulated software that does some system calls. It's basically this weird blob of assembly code where libraries have just been linked in there together. There's no clear operating system abstraction, and also the way those devices or the firmware talks with its sensors and actuators is not obvious, right? Often these interactions are done with direct memory reads or memory writes. And so, okay, so you have a piece of software and reads and writes from memory. Like, where's the input? How do you even get input into this system? So it's very complicated in the way this firmware is typically tied to hardware components that make up that device. It's not clear how you even get input and output into this device. And there's this huge heterogeneity where all the different peripherals and processors and microprocessors on this device are different. It's not, like the Linux system call interface is a clear standard that everybody understands, and you can use this abstraction. But if you analyze embedded devices, there are no such abstractions. So it's very complicated from that point of view, which again makes different analysis techniques necessary. We have some interesting interactions. When you build a system, it's often not just one device. You have multiple devices that can work with each other. There are, smart device hubs where you have the devices connected to them, and then maybe you control these devices via some application on your phone, and maybe not directly through this application, but through some website like if this then that, where you set up little scripting languages that take input from one device and send it to some other device, right? And then you have Alexa, and you talk to Alexa that speaks to a web page, it speaks to your mobile phone, it speaks to a security hub that speaks to an IoT device to turn on the light, right? So it's a very complicated ecosystem. And whenever you have different systems that need to interact with each other and different vendors and different protocols, there's a lot of opportunity for mistakes, especially in the security world, where someone makes some assumptions about something and another vendor makes somewhat different assumptions, and because they meet somewhere at some interface, if these assumptions don't match, it's just ripe for security problems. So, very, very interesting from that point of view. We have the problem of patch management. Sometimes you can't patch these devices. So even if you find the vulnerabilities, how do you update them? If a vendor has put out the device and goes out of business, there wouldn't even be someone who would want to update the patches. You have the problem of remote accessibility and authentication, for example, with a pacemaker, like, okay, you want to protect your pacemaker from people just messing with it. But if there is an emergency and you want the doctor to actually do something with it, you don't want the doctor to go through some long authentication process to prove that, yes, they can actually make some adjustments or give your heart a little jolt, because by the time they bypass the authentication and you're dead already. So the question is, how can you solve this problem to give certain people access fast, while on the other hand, still protect them from unauthorized access? So lots of interesting problems. In my opinion, it's a very, I think, fertile field of research, and it really sets new problems that we have not seen in, let's say, regular desktop or server software that make analysis interesting. So that's sort of the intro, and I want to tell you a little bit about how we've done some analysis for maybe not the most classic binary blobs. So we have started easy. We started with some Linux firmware, and I tell you a little bit of what we've done there. And then we dive into binary blob firmware, where we've done some different types of more dynamic analysis for binary blob firmware. All right, so let's start with the simple firmware. It's Linux-based firmware. After I've given you all the talk about how complicated it is, if you don't have an operating system, we sort of ease into our analysis. We actually first say, well, there's also a lot of Linux-based firmware where you actually have operating system abstractions and you have binary runnings on top of them. And you sort of have, your classic, some hardware peripherals, and you have your device-specific IoT code, the firmware code that you want to analyze. But the way this IoT code interacts with the peripherals is still through the Linux operating system. So you have that system call interface. And so what we found interesting about Linux firmware was, or what started the project was, that we said, okay, when you have that Linux firmware, you often don't have one program, one user mode program that implements a particular functionality, but you actually have multiple components that together realize some functionality, right? It's sort of multiple binaries, multiple components, user mode processes that run together to implement some functionality, right? And in the very easiest case, you might imagine on the right side, you have this IoT device, and on the left, let's say you have some control, let's say an app that runs on your mobile phone, and you want to interact, you want to maybe make the device do something, or you want to configure the device. What you do is you would send some kind of request. And for example, you could have like a little simple web server or some other border binary that takes that request, but it doesn't directly act upon it. It rather has a handler logic, and it hands over the request after it has then done some parsing to some other program that actually implements something device specific, right? And we call this then the handler binary, and that handler binary interacts with the device, and then let's say the actuator or the sensor, and then it gives back a response, and then it sends the response to the device. And so in this particular case, we have a simple two binaries that operate together to implement a piece of functionality. And what we sort of found is if you try to analyze these binaries in isolation, it's not exactly the right thing to do. And the reason is there could be a vulnerability somewhere in that handler binary. And the question then becomes, okay, so how can you get input into this handler binary, and what checks are done on this input before it reaches that handler binary, right? Because it's not just that the attacker or a user can talk with that handler binary on the right side directly. They have to go through that web server, and that web server can actually do some processing or some parsing that could make something that looks like a vulnerability in that handler binary not reachable or not triggerable, right? So the key the key insight of the analysis is that, hey, if you want to look for problems in this setup, you can't look at individual binaries. You cannot just look at individual binaries because you don't understand how input from an attacker, untrusted input, can potentially flow there, and what checks are done on these inputs before it reaches the handler binaries. So you have to basically analyze all of them together, and you have to understand the whole system data flow to really understand, hey, in this particular binary, this is how data can flow there, and this is because there's a vulnerability there, or no, this looks vulnerable, but the attacker can never reach it, or the input that gets there will never be able to trigger a potential, let's say, buffer overflow because it's checked in a previous binary that is on that path, right? And so what we really have to do is multi-binary analysis. And just to give you this example, so the analysis of individual binaries might miss bugs, or if you look for all of them individually and you assume unchecked input into each binary, you get a ton of false positives. So here you have the web server, right? And of course, we only have binaries, although we show you C code here. You basically have here on the bottom left, it serves a request, right? So let's say it gets some data that it parses from the URI, and then it you see here the parse URI function, for example. It might say, hey, does that input contain a string like this SOAP add rule? And if so, you return a pointer. You can also check if the size of this particular string is longer than 127. If so, you basically truncate it down to, you set the null byte, so you truncate the string and then you return the pointer P. And then you're saying, okay, well, how am I passing this over to that handler binary, right? There are different types of interprocess or IPC communication channels. Here in this particular case, you're setting that string into the environment, and then you would you start that second process, the handler process. And that handler process takes that query string out of the environment. And you can see here, you see query string is the variable that is where that first binary has stored the value. And then it gets a second value, which is called log path, which is also taken from the environment. But as you might observe, it's not taken from anything that the attacker can control. It's just an environment variable that is created when this IoT device is set up. It's basically a configuration value. And then you're processing the request. And what you do here is, for example, you check, is there some string op in there? And if not, you want to return, and otherwise you're basically copying some values, in this particular case, the query queue and the log path, into two local arrays. You see here on line 2 and 3, these are local arrays in that function process request, right? And in some sense, what you see here is like, okay, you have a string copy, right? That's an obvious potential problem that can lead to a buffer overflow. If you have a very long string, it gets copied into a local buffer that can lead to a vulnerability, right? But what is interesting is this here is actually a real bug, because it's possible that the input value in an unchecked way, if it has this SOAP add rule in there, actually gets into the query string environment variable, then gets copied into that arg buffer, and it can overflow it, right? But that second string copy here, it's also an unchecked copy, right? It's also something where you take some value and you copy it to a buffer, and you have actually not checked the length of the buffer. However, this is not a vulnerability, because in this particular case, the value for that log path that you copy over in logdir is also read from the environment, but it's not something that the attacker can control, right? This is some configuration value that is already given to you or it's created by the person who is sort of setting up this IoT device. So what you're seeing is that, well, if you would look at this binary, obviously there's no vulnerability, although a missing check happens here. And here that value is later used and it actually leads to buffer overflow. But if you would just look at this in isolation, we would find both line 6 and line 7 as potential vulnerable, and we would report 2 bugs, right? And of course you might say, well, if I report 1 false positive and 1 real bug, who cares? I found a real bug, that's great. The problem is, if you do this in the real world, you don't just find a few more false positives, you will find tens or hundreds X times more false positives, because a lot of this input checking and input validation happens actually in other binaries, right? So it's really important to track the entire flow through these multiple binaries to understand where do attackers put input into the program, how is it being processed and how is it flowing through these binaries, and where is it eventually used, and can it lead to a bug or a buffer overflow down the line, right? And you want to precisely track those data flows through these multiple binaries to make these decisions. All right, so how do we do this? Well, you know, we are sort of saying we're looking at certain binaries that can set values. We call them set the binaries or producers. You have get the binaries that are consumers of this data. And the idea is to find those bugs. We want to track how user data is introduced and propagates across these different binaries. That's sort of the task. And we've built a system to do this. It's a static analysis system that operates on Linux binaries and then can track those data flows across different IPC, inter-process communication routines, and within each binary, and it tries to find vulnerabilities. So in some sense, it's a somewhat traditional static binary vulnerability analysis problem that we've expanded to look for these multi-binary data flows. And you know, I'll sort of walk you through how we did it, and then I'll explain a little bit of why it was important and how the results look like. So first, we want to discover in some way what we call border binaries, which is where can user input actually be put into this system, right? This is not clear. Let's say you're given a Linux firmware and it has 5,000 binaries on it, right? A bunch of them are just part of some distribution. Others are maybe specific binaries that are programs that the IoT vendor has written, but it's not clear who is talking to the user and how could an attacker potentially inject any data into this, right? So first, we have to identify which are the binaries that can get potential input. Then we want to understand how those binaries can possibly pass information to other binaries, right? Also, that's not entirely clear. How do you do this? Like, how do binaries typically talk to each other, right? They can do it through the file system, through sockets, through shared memory, through the environment, as we have seen before. So we have basically to track all the possible inter-process communication channels to be able to track that. And when we do this and we can track those data flows, then we want to see if we can find vulnerabilities that happen as potential misuse of the data. Okay, so we have the system. Again, we're trying to detect the border binaries. We try to track flows. Then we do the actual data flow analysis using a static taint engine. And the goal is to find some vulnerabilities. All right, so how do we detect border binaries? It's somewhat heuristic. The idea is we're assuming that the first entry into the system is through network, right? So you have to have these binaries that receive some data from the network. And what we also assume is if you get data, if there's a program, a binary that gets data, we assume that it does some processing, some kind of parsing on it, right? So the question is, can we recognize binaries that seem to read data from the network? And, you know, on a Linux binary, that's fairly easy. Does it have the right system calls? Like, you know, socket calls to bind to a socket and receive and read data from it. And then can we recognize functions that seem to show that they are parsing some input in some interesting way? And what we basically do is we're having a fairly simple classification problem here, where we have some features like, okay, how do you recognize parsing? So typically there should be a bunch of comparison operations, there are a bunch of branches, there's some network related keywords, there's some data flows between a receive operation and some memory comparison operation. That's how you typically do parsing, right? You get some data and you start to compare it with stuff that you want to check for, like, is it a magic value? Does it have these keywords? And so on, right? So you're sort of processing, you're doing some somewhat more intense processing on data that you get from a socket. And so we are using these features. We took some features from related work. We added our own features. We built a very simple linear classifier where we just have some weights. We add all this up, and then we basically get a score or a weight for each function in a binary, and then we basically take the maximum value for a binary as the value for that binary. And then we could say, well, let's compare to some threshold, and if it's bigger than 42, it's probably a border binary, right? That's somewhat less elegant. We can do a bit better. Instead of having an actual threshold, we can start to cluster those binaries based on their scores, and we can observe that we actually see typically most binaries have fairly low scores and they cluster around very low scores. And then there is typically one cluster that really sticks out and it's very different from all the others, right? And we found, intuitively and empirically that really represents those border binaries very well, right? So don't have to have a threshold. We just do this clustering. We find those border binaries. All right, with those, we can start to build binary dependency graphs where we start to do the data flow tracking. And the question now is, okay, so how can you do this? We are looking for inter-process communication. And again, if you look at this, like typically they're just like a finite set of primitives that you can use on a Linux system. I mentioned, files, environment, shared memory. So that's the one thing. And the second insight is if you actually want to build a communication channel between two binaries, they sort of need to know about that channel, right? It's like, if I talk to another binary, I need to know what is the file name that I use to pass you data, right? And both the producer and the receiver of the data need to know this, or what is the socket number that we're going to use, or what is the name of the named pipe that we're going to use, right? So typically there are some keys that are essentially the names of this IPC channels, right? And so why don't we just look for those, right? So if two binaries want to communicate, we assume that they must know the name, that data value of the channel. So we can basically just go and say, well, they're either hard-coded in a binary or they come from configuration files that are also hard-coded. In this particular case, and the example that I showed before, would be that string that is called query string. That is a data value. It's the name of the channel. And we've seen that both the producer and the consumer knew this. So we're basically scanning for IPC primitives. We determine, is this a read or a write operation? We try to extract from that binary using static analysis the name of the channel. And then we're basically saying, if you have a producer that uses name X and you have a consumer that uses also name X, connect them. Easy enough. So we'd connect these two. Then we build a graph based on these edges. And when we're looking this, and this is on some hundreds of IoT devices, we basically see, okay, so when we look at the sizes of these graphs, there is one distinct value here. That's 1. And that means it's it's just the binary itself that doesn't talk to anyone else. But then you're starting to see, well, these graphs are actually real. And there are many of those sort of communication channels where you have multiple binaries that operate on this data. So in some sense, if you wouldn't see this right side, the whole analysis or paper would be useless, right? You could have just done it directly on the individual binaries. What we're saying is no, that actually in 2/3 of the cases, input is passed on to other binaries, and hence it's important to track this. And you cannot just look at the border binaries because you miss a ton of bugs, and you need to understand how those other binaries get involved. Right? And that's for 2/3. And as you can see, sometimes they are really big. Up to 16 binaries are involved in processing essentially one request, where from a border binary, it starts to spread. So then we start to do some multi-binary data flow analysis, start from the border binary. You taint values, sort of fairly classic taint tracking, where you mark a certain input as relevant, and then you track the code and you try to understand, are there operations in the code that take this data, operate on it, move it somewhere else, write it to results, right? And so you're sort of tracking the flow of this interesting data through the binary. So we're basically doing a forward taint analysis, and we collect constraints on it, right? We're saying, okay, so here's been some input that has been read and it's checked. Maybe there's a length check, or it checks that certain input characters are removed, or we check that particular constraints of the input are applied so that the attacker's freedom is limited, right? They cannot inject arbitrary values because the program is checking, it applies constraints to it. And that becomes important because if we later find a sink, a potential vulnerable place in the program, we can use these constraints and we can say, well, that is only a buffer overflow if the attacker is able to inject a string that is really long. But if the program has checked its size before, then it's not a vulnerability because we know the attacker cannot inject such a large string. Or if you're looking for an SQL injection, a database query, if the program first checks that certain things cannot appear in this query, the attacker cannot inject data and then cause a problem, right? So, we basically continue this analysis. If there's a setup point in this graph, we basically continue the analysis in the other binary, and we can start to basically really create this multi-binary data flows, where in this particular case, right, so we would basically say, hey, here's some unconstrained pointer P that comes. So here, it's basically, there would be some data that comes from some socket operation. It goes into this function. We find out, hey, there's no constraint to it. It returns the value P directly. P goes into that setter function. We track it over to this other binary. We start to continue our taint analysis from here. We track it up there and we say, yes, that it is possible for the attacker to inject some information that leads to a potential buffer overflow over there, right? So we check whether tainted data can reach a sink in an unsafe, unconstrained way. We're looking at mem copy-like functions, so buffer overflow access or buffer accesses and dereferences of pointers that could also be used for the attacker to, if you can influence the value of a pointer that gets later dereferenced, that's typically not a good thing, can be used to cause some security problems. So we're using a system that is built on top of symbolic execution, where we can collect these constraints, and then we analyzed a bunch of firmware. And we had two different data sets. One was like a smaller set of around 50 samples from 7 vendors. And then we got from a bigger data set from related work from Firmware, which was, about 900 binaries. And generally, I think it worked quite well. So here are some results. I don't want to go like super detailed into them, but you see here the seven vendors, where we had a total of 53 different firmware samples. And you see here, there are quite a few binaries, right? So there are like about 8,000 binaries. We found about 87 alerts. So, we started with these 279 border binaries. We started to explore, in total, sometimes the border binary was the only thing to look at. In other cases, when we had the graph, we went deeper into it. So think of it as a factor of 5. So there were probably a few hundred binaries that we analyzed out of these 8,000 that could potentially get user input in any way. And then we found about 51 bugs out of these 87 alerts, right? So it's a decent number. It's, about 2/3 of the alerts were true positives, were real bugs. Bunch of others were false positives for a variety of reasons. But I think two things are interesting here. One is the actual number of multi-binary vulnerabilities. So they were not in the immediate border binary with 34. That's again about 2/3, right? That's the number also where, 2/3 were actually multi-binary. So it is important to track into multi-binaries, otherwise you miss binaries. You miss problems. And we also analyzed all these binaries individually, just to say, hey, okay, so it's good to find more bugs, but what if we had analyzed them individually? And on the bottom, you see that produces 21,000 alerts, right? So this is then 30 bugs out of 21,000 alerts, which is significantly less great a yield, because then you have so many false positives that you would ignore it. So what we are basically saying is, yes, 2/3 of the bugs were multi-binary bugs, and if you would just sort of simply analyze each binary individually, you get 20,000 alerts, and that of course is an unacceptable false positive rate. So it's really useful. And similar things held for the large binaries. So you can see, just the numbers are bigger. It's 900 binaries. So again, somewhat in this case, half were had multi-binary data flows, and we had a total of 140,000 binaries. and we found about 1,000 alerts. So 1,000 alerts were produced among these 1,000 binaries. Here, we did not look at all 1,000 of them. We just basically manually inspected 100 alerts, and 44 of them were true positive, and 30 of those 44 were multi-binary vulnerabilities. So again, about 2/3 multi-binary vulnerabilities, and you have true positive rates of about 44% to 65%. So a good number of reports are actually true alerts. And we thought that's good, right? I mean, you just analyze it and you find 1,000 bugs. Okay, let's say half of them are real. So 1,000 alerts, 500 real bugs in real world firmware, just like that. So we thought that was exciting and really showed, again, the security of these devices is just not as developed as we would like. All right, so that was Linux binaries, and you could say, well, you told me how hard it is to analyze binary blobs. Now you do Linux binaries. It's kind of lame. So I still think it's exciting, but what if you want to look now at actual binary blobs, right? So let's talk a little bit about that. Here, that nice little Linux penguin has disappeared, and we basically now have just a firmware binary talking directly to raw hardware peripherals, right? And so we're assuming we get that binary, and now we have to do some stuff with it. We want to analyze it. And, how can you analyze it? Well, we can use static analysis, but another analysis that is often very useful and very powerful to find bugs is fuzzing. So let's see if we can do dynamic analysis. I don't know how many of you guys know AFL. It's the American fuzzy lop, which is actually the name of this rabbit, but AFL is also the name of a well-known fuzzer that basically just throws inputs at programs and watches them crash, right? So makes lots of copies, throws a lot of input at those. It's a coverage guided fuzzer. It tries to understand, okay, what of my inputs explore new code? And if there are some new code explored, it will focus on those paths and those inputs to try to cover as much of the program as possible. The problem is, like, okay, so now you have this binary blob and you have this fuzz, and you want to apply the fuzzer to the binary blob. But how do you do this? If you want to run the IoT device itself and you try to fuzz the IoT device directly through the normal regular input channels, that's a problem because you're sitting on this device, and how do you even realize that the device has crashed? How can AFL get any information about coverage? Like, how do you know what path did you explore? Like, you cannot monitor the program while it's running in the device itself. So you might say, well, can we just pull out that firmware and run it in some kind of, I don't know, maybe virtual environment, right? Some kind of QEMU style virtual environment where we just run the firmware and we just fuzz it, right? And the problem is, yes, you can, but what happens if that firmware code makes requests to the periphery, right? So if you just give it some input, you run it now in your virtualized environment, think of like a virtual machine. And now that code wants to talk to its sensor and read a value. But there is no sensor, right? We're in a virtual machine. So what are you giving it back, some random value, or you're just skipping that code, this sort of call? You quickly realize the firmware doesn't do much if it doesn't get reasonable values from its sensors and actuators. It would basically either just crash or it doesn't do anything. And it's not really a good representation of what's actually going on the real device. So now we're sort of at the conundrum. We cannot run it directly on the device because we can't monitor it properly. And also we cannot spin up 1,000 instances because it's just one device. You can just have like virtual 1,000. But if you want to run it on virtual devices, you want to spin up many, that firmware is like a bit disconnected from its own reality, right? You basically put it in a different environment where it might just crash, it cannot interact with peripheral, it just can't operate properly, right? So the problem, what we would like to do is we would like to rehost it, right? We would like to transfer it, like this binary, into some emulator. So we would like to do that, but we will need to somehow create a realistic environment inside that emulator that sort of makes that firmware believe that it's running on the real device, at least to some extent. So think of it like the enterprise holodeck. You're taking it in there. It thinks it's running on the real device. Everything looks pretty good, but you're actually in some virtual environment where we control everything. We can monitor the execution of the program. We can understand if there was an illegal access somewhere that is a real crash. And we can basically, for example, use a guided fuzzer to do to drive the execution the way we would do with a normal program, right? And so, how do we do this, right? How can we create such a holodeck? How can we create such an environment, right? So one way in which you can think of it is, okay, you just handwrite plugins for those peripheral devices, right? You can say, well, I don't have a real sensor. Can I re-implement that sensor in software and sort of rewrite its functionality of that hardware piece in software as a little plugin? So when the firmware device wants to talk to the sensor, it doesn't talk to the real sensor. It talks to a little module that we wrote and that says everything is okay, or it's hot in here, or something like that, right? And so that's possible, but as we will see, there are a lot of peripheral devices, and writing all of this by hand can be very complicated. Another idea would be, why don't we hand it off to the real device, right? There are ways in which you can bridge the firmware when it's running in an emulator and basically proxy handoff calls to the firmware. And there's a system actually from Eurocom, the Avatar, and that colleague of ours developed. Now there's Avatar 2 that can do that. It basically proxies calls into the real device and let the real device handle it, get the results back, and then continue the firmware analysis. The problem is that is nice, but when you start to fuzz, it's just too slow, and it takes time to do this proxying back and forth. And also, if you have multiple instances running, you can desynchronize your device, right? You have all these different executions going on in your virtual environment, and all of them are proxied into the same hardware device that gets like these weird requests that make no sense, right? And so typically what happens is just, crashes or sort of locks up pretty quickly, and then nothing works anymore. So we like software, we like those plugins, but real firmware is so diverse and complicated that you cannot write all of this by hand. You need some way of automating it, right? You need some way of automating that environment so you can present a software-based holodeck, so to speak, to the device. And that's what we started doing in this project. So here, basically, I just want to really impart this complexity of this interaction with peripherals, right? So you have a CPU memory, and then it accesses the RAM through the memory bus, but it talks to these on-chip peripherals, sort of little other microcontrollers that might talk to the sensors and actuators, also through memory, and it's called memory mapped I/O or MMIO, where basically you do reads and writes into memory and from memory that are basically mapped or backed by registers of these little MCUs, these microcontrollers that actually then talk to the real hardware. So, for example, you have some on-chip thing that then has, here some serial communication chip that would talk to, over the serial cable, or you have some IC2 buses, or you have some power configuration. So there are a lot of different memory pieces that are basically mapped to on-chip components that then talk to these off-chip components. And even for a timer, right, you might have like a lot of different registers that control different functionality or that can configure different things on those devices. So it's all different and heterogeneous and complicated, and it makes it almost impossible to do it by hand, but it also makes it hard to do it in some kind of automated way. How can we automatically generate software that can pretend to even be the timer in some realistic way when it has to somehow give meaning to all these registers? Because when the firmware interacts, it assumes that, well, register number 10 is whatever, some timer 5 SR register that has a meaning to it, right? And so that is a challenge here. So the question is, can we observe the real hardware and automatically learn models for our emulator, right? That's what we would like to do. And the system that we built to do this is called Pretender, right? So we want to pretend to be these real devices. We want to pretend to be the real device to that firmware. And so the way we're doing this is we're basically saying, and this is, a very simplistic way, you will say, yeah, well, but that seems pretty simple, as you will see. But basically, it's a first start. Our first start is we're recording. So the general approach is we're first recording interactions between the firmware and the real device, like avatar style, right? Where we say, okay, we start not in this big 1,000 instances fuzzing, but we start with one instance in our virtual environment, and we're basically letting it run, and we try to stimulate it, and we try to monitor the interactions with the real device through this proxy-based system, which is Avatar, right? And then the idea is, can we, based on these recordings, can we basically extract or learn how these interactions seem to work, and then sort of imitate or pretend, replay them almost, but a bit smarter than just replaying them in software, right? So that's how Pretender was operating. So we're basically recording things, and we want to record the interactions between the firmware, the gray piece, and the internal peripherals, this sort of green piece. And the way we do this is, as I mentioned, we're recording using Avatar. So on the left side, this is running the firmware in an emulator like QEMU and using Avatar to proxy the calls directly to the real device and record this interaction. And when you have that recording, then you try to do some modeling. And the modeling works like this. You first try to understand which are sets of MMIO registers or regions that seem to belong to one device. And you do some clustering, and you try to understand, okay, this set of registers or this set of this memory region seems to belong to a certain device. Of course, you don't know what the device is. You have to deal with interrupts. I'm setting that aside, but there's a complication because there are continuously asynchronous interrupts happening on this device, and you need to model them in a reasonable way as well. But what I really want to talk about is, okay, so how is our modeling working? Like, okay, so now that we have this recording, now we know that there are a bunch of registers that belong to a particular device. Can we build a simple model that might allow us to build a simple software-based model for that peripheral, right? And so how do you do modeling? The way we're doing this is, first we observe that some registers or some interactions are of some very simple types. And sort of we're trying to recognize those types. For example, we observe that sometimes we say, okay, you read a value, some value, then you write to this value, to this register, and whatever was last written to this register is what would be returned on subsequent reads. So the firmware writes, and then it reads later that value. It seems to be getting back what it has just written before. So that seems to be some simple storage type of register, right? So we can build a simple storage model. We can say, yep, that behaves like a storage model. In other cases, we determine it's just write only. So that's a nice register because it just seems to write in and never reads anything back, so we don't care about it. So it's a write-only model. We can basically ignore values written to it. In other cases, you have some reads, and it only reads, and you find out it seems to get some recurring patterns back, right? For example, here 124, 124. So you model that, and you say it's a pattern model. It seems to read certain patterns. In other cases, that's often the case with counters or timers. They seem to be monotonically increasing or decreasing. So you can recognize a pattern that seems to be, an increasing or decreasing timer model, right? And then we have some other model that says, okay, but what if it's not one of these known models? What if it's more generic, right? So here, for example, is one where you can write, and it can write a T, and then it reads like 72F for 72 Fahrenheit. And then you can write an H that says, give me the humidity, and you do 67%. And then give me the temperature again, 74 Fahrenheit, right? So in this case, it actually reads the temperature like digit by digit, and then, this F for T. So how would you do this, right? There's no obvious pattern here. This is like some, let's say, more complicated semantic. So what you can do here is basically you can do some state approximation. So you're trying to approximate what you have seen during the recording in some somewhat cleverer way, instead of just saying, hey, I replay exactly what I've seen during the recording, but you try to build like a very simple state machine. And it's really a very simple state machine. So can we recover the entire true state machine? Obviously not. There could be very complicated physical processes behind it. Could we just guess and return some random values? Yes, also, but it's just less effective. It's better to just try to use what you have observed during that learning period, and you try to build some simple state machine that tries to approximate this as well as possible. So what we're basically doing is we're saying, okay, so every time the firmware writes to that register or to a register, maybe that is something that might change a state. So we consider this a state changing operation. And when subsequent reads happen from this register or related registers, we consider this reads from the same state. So we're still in the same state, and we try to replay the values that we've seen it reading in that state before, right? And then whenever there's another write, we're sort of saying, well, it changed the state. So when it reads, we're basically having a pointer in the trace that we have recorded, and every read, we're just basically returning a value from that trace until we hit the end, and we just stick at the last point. And whenever there's a write, we go to wherever we have seen in our trace that has been recorded, where that value has been written, and we're basically switching our state machine to that state. So I can give you the example here just to show this. So in this particular case, every write starts a state, right? So this would be our states. And then if you have these transitions, when you write an H or a T, you jump around from these states. And when you are in a particular state, and as long as it reads, for example, if we're in this state and it reads, we would return 7 for F, until there's a next write, then we jump somewhere else, right? And it's very simple, but it actually worked reasonably well as a first attempt, right? And I think there's a lot of interesting machine learning based models that we can build on top of this to expand it, but we started with a sort of that more basic approach. And what then we did it, we looked at this, we looked at 6 firmware samples that were somewhat simple on an embed framework-based board. And the peripherals were real, stateful, they had interrupts, and we injected even a couple of synthetic vulnerabilities in the firmware. And what we then did is we basically said, okay, so you have 3 boards, the Nucleo and then the Max, 6 sort of sample or 6 applications, I would say, simple like hyperterminal or a thermostat or a door lock that have different peripherals. And we started to record. Here's sort of a basic blocks recorded. You see models that we built. Here's the state-aware models, or rather, I should say. So this is the blocks that were visited while we did recording. And when you give a dump model that would always return a null or a random value in the testing, you can see here how the number of blocks that you can explore dramatically drops, right? That firmware is just not doing much. Instead of hundreds, you get 8 blocks, because on the first read, it just errors out because it gets some real value that it doesn't expect. And if you do some state-aware replay, so with our simple state-aware models, you can see that we actually get back pretty close to the original one, right? So this, like here's like 280 blocks that were visited when we replayed using our state-aware model. This is during the recording, so you basically get almost the same code coverage. That means the models replay meaningful values that allow the firmware to run in our virtualized environment, right? And we can even fuzz, at least those 3 where it allowed user input. And what we can see here is that in some cases, we're even exploring, visiting new code blocks that were not touched during the recording, but our state-aware models were able to keep the firmware going and thinking it's running reasonably well, so that it was not just immediately sort of erroring out or crashing, but it allowed us to explore different code and rediscover also the vulnerabilities that we have injected. So we're sort of happy with that. So the models enable us to perform what we call here survivable execution. So we could execute them and we were surviving and not just crashing left and right, because the inputs that the firmware was expecting were completely random. So, and we also were able to do some fuzzing with this, and we rediscovered the bugs that we have injected. And okay, you can see it's not very impressive. You put the bugs there. So I was like, okay, you can find them. Okay, but we did, so we were happy about that. So that was a pretender, and I'm somewhat late-ish on time. Let me talk about a couple of other things briefly, because I think they just round it out nicely, and then we'll wrap it up. So one is, this is an interesting piece, but the question is, can you do better, right? And I just want to tease a paper that we recently did, actually with Thorsten and one of the students that visited us, and that is trying to say, okay, so instead of injecting values based on looking at those recordings, could we try to basically inject the value first at random, right? And we've seen that doesn't work very well, but then use some kind of symbolic execution and track the value that you feed into the firmware and sort of try to see, well, what is the firmware really looking for, right? Is it looking for particular magic values? Is it looking for particular values in a certain range? Is it looking for a certain sequence of inputs that seem to keep it going, right? So you're basically saying, well, instead of just observing in some sense in the black box way the interaction between the firmware when it's running in a real environment, can we sort of feed it inputs and track how these inputs, like what do these inputs do in the firmware? Does it, always take a certain branch? What would we need to feed it to take another branch? What would we need to do? What are the bits that are relevant? What is the firmware looking for in input, so to speak? So you're basically looking at the firmware itself and the code, and you're looking at how it processes some very specific inputs to try to understand which inputs you should feed it to make it explore the right parts of the code, right? And so the way we do this is we are using symbolic execution, where we're basically putting some data into the firmware. So the firmware reads some input from, let's say, thinks it reads it from a sensor. And we're giving it a symbolic value, and we're now tracking how the firmware processes this symbolic input to try to understand what are interesting ranges or values that we should feed it in order to make it continue or to make it do reasonable things, right? And so that was sort of like a flipping it around. Instead of just observing what it does, really use the code to drive the inputs that we think it wants to get in order to keep going, right? And that worked actually really well. And so you can see here, and again, this is like a super big dump of a table. I don't want to give too much information, but what I do want to point out is, so we did these tests and we actually ran them not on these like simple like boards that I was talking about before in Pretender, but now these were like more complicated firmware for real IoT devices. Again, you have like GPS tracker, thermostat, 3D printer, some network socket operation. So these were like real. And what you would see is, okay, the basic blocks, right? So in top you have BB, in target, minimum, average, maximum, total, and so on, evaluated. And what you would see is that we compared to a number of other systems like P2IM and MicroEMU and our own stuff. And we saw that we would typically explore more basic blocks than any of the prior work, right? So feeding the right inputs really allowed us to explore those firmware deeper than prior work. And what we also found is, in this case, real world bugs. It was not just the 3 bugs that we injected. So these were actually real bugs in, this is Contiki. That's, I think, some networking library. This is Sapphire operating system. So these were sort of, not like super big, but reasonably big real-time operating systems that actually were buggy. And, FW stands for fuzzware. That's the name of the paper, was actually exploring broader and finding again, really interesting bugs. And what this shows is that this idea of sort of taking it out, rehosting it somewhere else, and then exploring it in sort of this holodeck, in this virtual environment. If you do this in a clever way, you can really use somewhat existing powerful analysis techniques like fuzzing and find a lot of bugs. The hard part is not like the fuzzing here. The hard part is like make that firmware do stuff when you're in this virtualized environment, right? And so both Pretender and fuzzware were ways of doing this. So we're excited about that. So that was one of the things. And then let me just give you one more thing, like the Steve Jobs thing. There's always one more thing. I just want to point out that we basically chose in those 2 projects to emulate at this level, right, between the firmware and the hardware peripherals, right, and those MMIO calls. And what we have basically observed is like, hey, this is a really complicated, diverse interface. It's very hard. Can we go one level up? And sort of, can we, even in these binary blobs, can we recognize that they have libraries too? There are development frameworks that actually are used by people who build embedded devices. And even if it's not Linux-based, even if it's binary blob-based, right, where a vendor, a hardware vendor, might have a bunch of hardware peripherals, but they put a hardware abstraction layer on top of it. And on top of this hardware abstraction layer, you actually might have, you know, protocol stack libraries or peripheral libraries. And only on top of this, you write the device-specific IoT code, right? It's not everybody that writes an IoT device like a vendor has to redevelop everything on top of the hardware peripherals. What they typically get is at least this, or maybe all the colored thing, where they're building their stuff on top of at least the hardware abstraction layer or on top of some protocol stacks. So instead of emulating this really hard thing, the question is, why can't we emulate this, right? Why can't we recognize library functions in the binary, and then instead of giving you, in some sense, a software re-implementation of the device, we're basically giving you a re-implementation, a simple software re-implementation of the library, right? Let's say of the IP stack, or of an abstracted hardware peripheral that has some much smaller, much more well-defined interface, where the implementation behind it is much, much simpler, right? And so that is the system that we built, which was called Hallucinator, which basically did high-level emulation, right? So we're basically, in this particular case, we're having, as usual, emulator PMO, and then instead of having hardware models, we're basically having replacement models at the level of the HAL, or at the level even of the entire libraries, right? And so that was that system, right? So it was called Hallucinator. It was an HLE, this hardware layer emulator, and basically replaces these HALs or libraries with high-level implementations. And then the rehosting problem is no longer re-implement or automatically generate 10,000s of device models, but re-implement maybe a dozen or so library functions. And then you can actually run a lot of that hardware in that environment as well. So that's what we did. Again, I think it worked really well. I know I'm sort of a bit low on time, so I just show you a result here. Let me briefly scroll there. Now that's the bindiff stuff. So basically, again, right? So we ran fuzzing on top of it, and here was some crashes that we found from prior work. Again, real world, you know, big firmware devices, and then we found, you know, new bugs like use after free and double free bugs. These were some outdated IWIP versions, buffer overflows that someone was actually trying to fix a buffer overflow, didn't work, so we found it again. There were like 2 CVEs and a number of other previously unknown buffer overflows, right? So that also really worked, right? So you could basically take real-world firmware, you put it in this hallucinator system, and by just emulating the library functions, you can, you know, use fuzzing to find those real bugs in these firmware samples. So in some sense, it's a matter of taste what you want to use. Generally, Hallucinator, sort of the hardware abstraction layer that replaces the libraries, has the advantage that I think it's simpler to implement, and it allows you to explore the firmware binaries really in great detail. The only problem that you get is you might miss any bugs that are in those library functions, right? Because in some sense you have replaced them. While in the other, like the fuzzware approach or the pretender approach, you're basically examining the entire real stack up until the MMIO hardware interface. So both work, both are interesting, both I think are still, some active research. As I said, like Fuzzing is about to be published. Hallucinator came last year. We have some follow-up work also. This is actually together with Matthias Payer from EPFL. So, it's interesting, sort of interesting research where we definitely have not reached full maturation yet. All right, I think I'll stop there. I hope that was interesting. If you have any questions, feel free to go. Thank you.
What is the German way of
I know that. Yes, no worries.
If there's anybody on the Zoom call who wants to ask questions, I tried to monitor the chat. Otherwise, if there's anybody here who has questions, here we go.
Go for it.
Okay.
You mentioned multi-binary bugs.
Mm-hmm.
And you showed us examples that you find far too many bugs if you look individually.
Mm-hmm.
But if I heard you correctly, you also mentioned that it could happen that you don't see any bugs individually, but collectively something might happen. Or did I misunderstand that?
Yeah, so, okay, what I meant is, and so you're right, I guess, if you would look at individual binaries, you would find a superset, right? You would find all the bugs you would find individually. What I meant is, if you limit yourself to just the border binaries, right? So people would say, hey, I just look at those that receive inputs directly. I'm just looking at those. Then you miss everything that is behind, so to speak. Oh. Yeah, no, makes sense.
Messenger.
About the first part, about the static analysis of Linux systems, it would seem to me that this entire approach could get quite easily confused by a sort of Unix-style construction of the system. So consider a pipeline where a lot of binaries like Unix cat and grep and sed and whatever are integral parts of the pipeline. There's nothing interesting about these binaries themselves that gives information about how they are used, but there could still be a lot of bugs that result from the specific usage of these binaries. So my question is that an actual problem in practice, or doesn't it just really happen that pipelines depend on these sorts of constructions?
Yeah, I mean, I guess what you're saying is that the bug is not like an implementation vulnerability in a binary. It's basically, okay, you're putting it together in a way that maybe the system is put into some state that you don't want, or maybe the attacker gets some access to data that they shouldn't because you just decided to cat the file, right? And yeah, cat doesn't have a vulnerability, but it still allows the attacker to access, let's say, a database. Yeah, I think this approach would probably not work because we're looking particularly for, implementation vulnerabilities in the binary, in the program itself that is triggered by, these data flows. I think what you probably want to do is you're sort of saying, okay, so who is orchestrating these binaries, right? Are there some scripts that would put this together? And then you would probably analyze that orchestration script and you're saying, okay, is there something when I execute the script or when I, run those binaries in a particular order that certain security property is violated, right? It's like, okay, maybe I should never access a certain secret file, but with this input, I can trick ls to do something with cat that gives me that file. So I think it's interesting. I think it's sort of a slightly different threat model, different setting. I don't think I've seen this setup much, but I can see why people want to write bash scripts to put stuff together. So it certainly could happen.
Thank you.
Yeah.
Other questions here from the audience?
I would be curious how they test IoT system in production. Also, when they build them, how do they write tests?
Yeah, it's a good question. I mean, one, if you're the vendor, typically you have source code, so you can run some source code static analysis. I mean, like Fortify or whatever, right? So you're doing like secure lifecycle development, your typical software testing. And a bunch of these guys have boards, development boards, that work a little bit like Hallucinator, where actually the hardware vendors of the boards give you implementations of like libraries or implementations that are essentially software implementations of these actual modules. Mm-hmm. So you would write it on developer boards where some of these models are written for you in software, but those actually are fairly heavy guarded and very expensive. So they wouldn't just give it to you, right? You sort of have to be like, you have to show that you're an IoT vendor to the vendor that makes those peripheral devices, right? And say, I want a board, right? Can you give me a bunch of these boards, right? And then, yeah, you pay tens of thousands of dollars. They give you the boards, and then you have some software simulator or emulators that allow you to develop some software against the hardware.
Go
ahead, yeah.
You said when the devices get wrong input, they immediately crash in a lot of cases. Is this like a desired case? Is this desired, or is this just they don't anticipate that there will be wrong?
Yeah, it's the latter, right? So if you know, okay, you read the spec, and then basically it says, okay, this is the semantic of the register. I'm expecting values. If you have a little protocol, it says, okay, first I send you 1, you give me a 2 back, right? Then I send you a 3. So when you send random values, it immediately says, okay, this is completely weird. I mean, it doesn't always just crash. Sometimes it just goes into an error state. Often those error states are not easily recoverable. So then, you have to actually reboot the device in the real world. But when you do it in software, it just sort of locks up, and then it's in some kind of error state where you can't get it out. So yeah, it's in some sense it's, I guess, a result of not super robust software engineering on the behalf of the firmware writers, but you can also understand why they do it, because they get pretty reasonable specs, and then they don't just expect those random values.
Okay. Thank you very much.
Other questions from here?
Regarding those calls from the server who checks the length of the string, couldn't this be kind of corrupted in a way, or you're thinking of everything working properly? So you're in a model where the attacker is the bug.
Well, the attacker is the bug, yes, but we don't assume the checks to work properly. So let's say you don't implement the check properly, you forget the case, or you can bypass checks, we would find it too. That is sort of when the constraints come in, right? So the checks would say, well, the length cannot be longer than this on this path, but on this other path, it could be, right? So then we're saying, yep, if you give this input, we find this path, then you're not bound by the length. And if that string is sent over, then you can exploit the buffer overflow, right? So we don't assume checks work. We're basically saying those checks constrain the inputs in some way. And if we manage to find a path through all these constraints and all these checks, where it eventually is being able to trigger a bug, we would find it.
And that was actually one of my questions too. So, but your assumption is that let's say the border binary, for example, is not compromised, right? So,
yes. Sorry. If that was the question, yes. So the attacker essentially is remotely interacting with the system, right? So it sends you web or network requests. If you have them on the device, then it's like, okay, at this point, I won as the attacker, right? Or are you saying like a supply chain attack where they try to subvert the binary?
I think it was more from a theoretical perspective that your assumption is that none of the previous binaries is compromised.
The assumption is sort of the code itself is essentially, trusted. It's like an honest but possibly incompetent developer. Yeah,
cool. No questions at the moment. Otherwise, I have another one, which is I have several actually, but the quickest one maybe. So from a scientific perspective, so methodology, right? So you're developing tools that help to find bugs essentially.
Mm-hmm.
that's somewhat methodology development. Do you? And I saw that in some cases you say, okay, so we introduce our own bugs, so we know that these bugs should be found.
Mhm.
But do you have any means of verifying essentially that your techniques don't miss
bugs?
Yeah.
Well, first, we're not sound, so totally possible that we miss bugs. The way you typically do this is, just two ways. One is you take older versions of software that have known vulnerabilities, right? So you try to check that, or prior work has already identified certain bugs, and you're saying, okay, can I refine them? So it's mostly refinding existing bugs, and where you know that they're there, and then if you miss them, trying to understand why you missed them. That's really as good as we can. I mean, there's a lot of work underway that tries to put synthetic bugs into code, right, and then try to create some kind of fair benchmark. I don't know, maybe you're familiar with Lava. That was an attempt to put in bugs, especially for fuzzing tools, and then try to understand, okay, what are their false negative rates? Do you find everything? I find it's hard because what happens is, how do you get realistic but synthetic bugs into code that don't have so obvious artifacts that everybody who's wanting to publish a paper specifically picks up on all the artifacts that those bugs that are introduced sort of show, right? And that's what we saw with Lava. They put certain checks in there, so everybody was optimizing their systems to look for these checks and pass these checks. So it's a hard problem. So the way we try to do it is, yes, try to have known vulnerabilities in there and then see how many of them you can refine.
I mean, to some extent, I guess it's a bit similar to the whole intrusion detection systems in networks situation, right? Where it starts to be difficult to run scientific papers, since, I mean, there's a certain number of data sets available where we know what kind of anomalies are in there. And then
it's an excellent point for those who were not born at the time. Like in the late 90s, there was an attempt to build a data set from Lincoln Lab. It was called the MIT Lincoln Lab data set to test network-based intrusion detection systems. And they were also introducing attacks into this data set and then let sort of systems detect it. And, once you know where the problems are, everybody optimizes the system to find 100%, because otherwise, if you publish the paper, everybody will say, why didn't you find this, right? And this was actually at the time, it was still good, but it in some sense turned out, it had very obvious artifacts because the attacks were injected by a machine that was one hop further away than the legitimate hosts. So the TTL value of the packets of all attacks was one smaller than all the legitimate traffic. So there were machine learning systems that detected 100% attacks that were only operating on the time to live, the TTL field in the IP packets, right? So it says, when the value is 60, it's bad. If it's 61, it's good, right? And so it just shows you have to be very careful if you put artificial attacks in there that doesn't have artifacts the defense systems can pick up. Yeah.
I think there's a question on the call.
Okay.
Could it also be possible to connect the debugger to the device and the debug pins are not removed from the board to do on device fuzzing? Or it's just too slow or sufficient enough to get coverage info?
Yeah, so I mean, the classic debug board or JTAG, sometimes it's there, sometimes it's not. I think the biggest problem is not so much that that debug interface is too slow, although it's also slow, but it's when you start to then do these interactions with the actual peripheral devices, there are some delays introduced that really slow the fuzzer down. So it's less. Would the debug interface be too slow? Maybe, but probably okay. But once you actually interact with like real physical peripheral devices, they are very finicky and they are introducing delays. And you also have this interrupt problem that I haven't only like very briefly touched, but you have these asynchronous interrupts. And if you start to slow down the device a little bit and the interrupts are starting to get missed, this whole thing just breaks down and nothing works anymore. It's really very brittle. So yes, that's a way. Sometimes debug and JTAG interfaces are there, but I don't think you can scale fuzzing reliably on the real device.
Cool, thanks. I hope that was answering your question. There's another one regarding slide 28.
Okay.
Do you have an intuition on the gap on slide 28?
Oh, because we don't have any with 2, 3, or 4.
I guess.
No, that's a good question. I don't know. I guess this is just once you decide to implement a system where you have sort of multiple binaries, what you typically end up is you compartmentalize it in a way that you say, well, I have different modules or different binaries that handle different parts of the functionality. So having 2 might be a bit silly, right? Because why hand it off to just one other module? Maybe then you have 1. So you'd expect you want to have a certain amount of different types of functionality that you want to modularize. And I guess the number is 4 or 3 or before you start doing it. But that's guess.
Cool, thanks a lot. Any other questions here at the moment? Otherwise, I have a non-technical question or less technical question. We still have 1 minute, I think, so that should be fine.
Good.
So why isn't industry doing anything? Or I mean,
why is industry? Well, I mean, I think the industry. I mean, it's the usual thing, right? I mean, it's an incentive problem. It's time to market pressure. I'm sure they're doing some functional testing, but if you're not liable for the impact of bugs, and people don't demand certification or just it's just a money problem, right? So I think it's really it's an incentive issue that costs you money and slows you down to market. So why would you want to do it?
Do you see anything happening? I mean, is industry starting to cooperate more? I mean, we saw the same with the operating systems, right? Microsoft used to be terrible, and then
decided it wants to be good.
Yeah.
No, I think for them it was starting to become a real business problem, right? I mean, all these worms in the beginning of the 2000s. I mean, it was such an insecure platform that I think there was a lot of pressure on them saying, we're not going to buy your stuff. And so I think they sort of embraced this. I think there are definitely efforts underway, certification efforts where, maybe, in order to pass the certification, you have to at least demonstrate, certain practices, or it's tested by some third parties. And then if, for example, large organizations or governments say we're only buying it if it's certified, right now the vendors have to go. And I think this is sort of like the ecosystem pressure.
All right. If there are no other questions, then I would like to knock.
Great. Thank you very much. Sorry for going a bit longer. Thanks for staying.
Thanks a lot, Chris. And then as a follow-up, I think there's for everybody here. So for those people who would be here for the lecture, there's going to be a lecture next Friday, of course. For those people here for the distinguished lecture series, there's another distinguished lecture. I don't know exactly when. I think in February, with Angela Sasse, I think, giving a presentation. Somebody's agreeing.
It's on the website.
It's on the website.
I guess the 11th of February.
Yeah, exactly. Yeah. So that will be the next distinguished lecture. And for everybody else, for you, thanks a lot again. And for everybody else, have a nice weekend or a good appetit.